It's too close.
Yeah, I understand. Okay, let's get started. Welcome to Chem110, and we'll have PChem this quarter. Now, this is our week 0, so obviously we'll go over the syllabus first, and we'll kickstart some general terms, and we'll have the real material come next week after. Well, this week is also real material, but nevertheless, let's start from the syllabus. A few things on the syllabus. First thing is, as you probably see, I posted like a syllabus quiz. So make sure you get those 3 points by just reading the syllabus and answer some very straightforward questions, hopefully. A few things to highlight. So first of all, my office is in Young Hall 4222F. It's right outside the seminar room, if you know where that is. So I do have like an open door policy, semi-open door. So if my door is open, like you're welcome in to just ask any question you like, to stop by and ask anything. But if my door is closed, please allow me some concentration time if possible. And then I'll host like regular office hour every Tuesday. So that's also listed here. That's gonna be between noon to 1:30. We can meet in my office if the flow is not too big. I also reserve a separate room for you to sit in and just work with your peers and can come with questions and so on. What else? Yeah, everything here is pretty standard. You have the course material. Your discussion session is led by your TA, who is Miranda. She'll meet you probably next Tuesday in the same room, 11 a.m. as well. So discussion session, tutorial session, and these are not like mandatory, but it's highly recommended because your discussion worksheet is contribute to your grade, a significant portion of it. Course material, just your textbook. If you have a copy of your textbook, good. If you don't, we also reserve a free copy in the library, so you can go and check it out. What else? Grade course policy. Yeah, so the grading scheme is pretty standard. We have 35% to be your homework, and then 25 for your exams with 3% extra credit. Now this course is slightly on the harder end, so our grading policy is a little bit tilted already. So if you get something like a like 87 or higher, you'll get some flavor of A instead of 90. And for exam policy, all right, so all my exams are open book, open note. So that means please focus on trying to understand what we're talking about when we're having lectures. Also, like when you're working on your discussion worksheet, like don't try to memorize anything. Like that's not the goal. That's not how you learn physical chemistry. Try your best to understand what is the concept and how to use those concepts flexibly. And for exams, we don't curve specific midterm exams, but at the end of the quarter, if the class average is below B-, we'll curve everyone up. If it's above B-, we won't do anything. So it's not gonna hurt your grading anyway. What else? Yeah, so regrade policy, missed exams and quizzes, it's more like a case-by-case scenario. So just read it through and let us know if you have any special need. All right, and last thing, we have our course schedule. So in the course schedule, it is basically listed like what are the topics we want to go over. We'll start by like fundamentals of thermodynamics, and then we'll start talking about laws of thermodynamics. First law, second law, a little bit on third law. Especially we're focusing on lots of like seemingly abstract concepts, like what is enthalpy, what is entropy, and why do we care about them. So that's the overarching goal of our quarter. I also left it like several like selected topic. It's just because I tend to run behind my schedule. So if everything goes smoothly, we might have time to talk on maybe electrochemistry or solution phase thermodynamics. We'll see how fast we go. And one more thing is next Friday, you'll have a lecture by Professor Eric Wu. I'll be traveling for conferences. And if you had Eric before, he's a nice person, right? So yeah, and next Friday I'll be traveling and Eric will be taking care of you. All right, and one last thing before we move on to actual materials is the way to organize our course. So this is the first time I'm trying it. So on the Brewing Learn, we have 2 discussion boards basically. Well, more will come when we proceed throughout the quarter. So for any kind of like general question you have, whether it's administrative or like course related, I highly recommend you just ask it on here. So that, for example, if one of you is confused about the topic, then maybe your classmate is also confused, right? So ask your question on this discussion board is highly recommended. You can still email me if you feel like, oh, you want some privacy. That's okay, right? That's totally fine. It's just like I kind of encourage you to use the discussion board. Okay, any questions on, yeah.
So just to clarify, you're going to give us worksheet as like for homework assignments, so we
Yes.
don't, and then like you mentioned prior, if we have already a copy of the textbook, we can like opt out of like the access to the textbook?
Yes, I mean, the only thing I need from you is you have some kind of access to the textbook,
Okay.
because we will be using the textbook throughout the entire quarter. How you get the textbook, I don't care. Yes.
When you say open book on exams, do we need the physical textbook, or can we do it on the?
So for exams, unfortunately, only on paper. So nothing electronic is allowed. So you can print out your note, you can bring your textbook, that's all okay, just as long as it's not on an electronic device.
Print out pages of the textbook maybe?
Yeah, if you like, yeah. Okay, any other questions on these administrative things? Yes?
Are the tutorial and discussion sessions going to be recorded?
That depends on your TA. You might want to ask Miranda directly next Tuesday. Okay, if that's everything, I guess we're ready to move on to lecture 1. So this is going to be a grand introduction to term of thermodynamics. That's one thing we will cover. Basically, in our first topic, that's called terms in thermodynamics, we'll be talking about definitions of or vocabularies of thermodynamics that we will use throughout the entire quarter. And then we'll do a calculus review. So this class is PChem. So we will be using derivative calculus, integral calculus, partial differential equations, etc. I know that's already in your prerequisite, right? But it doesn't hurt to refresh your memory a little bit on the math. Okay, so getting started. What is the goal of today? So in general, if we're looking at systems from like very small to very big, right? So if we're looking at something like a carbon atom or maybe like electron, you'll get that. You need to describe those microscopic particles using quantum mechanics. On the other end, when we are talking about thermodynamics, we're talking about a macroscopic system. Right, so in thermodynamics, we really talk about like specific molecular structures. And for example, what does a molecule consist of? We're more likely to talk about like you have an ensemble of particles and how do these particles behave and what kind of macroscopic properties we will see. Like temperature is a very clear example of a macroscopic property. And then in the middle, we have statistical mechanics. I think you'll have a separate course for statistical mechanics and quantum mechanics. So this quarter, we'll be focusing on these macroscopic equilibrium. All right, and as stated in your textbook, we say like thermodynamics is the study of heat, work, energy, and also the change of, the change they produce in the state of systems. So getting started, we have several terms in thermodynamics. So again, these are just like vocabularies we will be using throughout the quarter. Don't try to like write out anything because I post all my annotated notes online and you have like videos to access them. So don't spend your time writing down, just try to focus on like understanding what these terms are. So for example, in thermodynamics, we'll constantly refer to a system versus surrounding, right? So when we say a system, that's basically saying that's the part of the universe that we care about, or this is a part of the universe that we are studying right now, Right? So for example, if I have this bottle of tea, I can say like, okay, I only care about the liquid inside the bottle. So everything else will be my surrounding. And the liquid in my tea in the bottle will be my system. Right? And then when describing a system, in this case, when describing the tea in the bottle, you have three different criteria. So depending on whether the transfer of matter or energy is allowed, you can have open system, closed system, or isolated system. So again, let's use this bottle of tea as an example. Right now, we have tea inside the bottle. Now the tea cannot come out because my cap is closed, right? So this system itself is gonna be a closed system. So when we say a closed system, we're saying like there's no transfer of matter, but there can be transfer of energy. Meaning like if I hold it for long enough with my hand, if my hand is warm, then the temperature of my tea will go up eventually. Or put it in the refrigerator, it will get cooled down. So the energy transfer is allowed in the process. So that's why we say this is a closed system. Now, what if I open the cap and now it becomes what kind of system it becomes? Open system, right? And for isolated system, that's more or less an ideal scenario. We will talk about it, but as a matter of fact, like we as human beings, we can't build walls that absolutely there's no transfer of energy. But when we say like a system is isolated, it's more like the transfer of energy is like so small, it's not significant. All right, so three different types of systems are available. And this is just one more example of like what is the system of our planet Earth. Obviously, that's an open system. And the milk in the box, right? That's my tea in the cup. That's like a closed, non-isolated system. So with that in hand, we can then move on to talk about kind of walls. So we've talked about open and closed systems. So like in this case, the milk box themselves has a wall that's separating the system and the surrounding. Right, so in this case, we have different kind of walls that we care about. So basically a wall, we call it a wall, it doesn't need to be a physical wall. It can be any kind of thing that separates your system from surrounding, or system A from system B. So we have, likewise, three different criteria to describe the kind of wall. Whether or not it is movable, so that's rigid versus non-rigid. You can have like soft wall that will move around. You can have permeable or impermeable, that says whether or not that wall allows matter to go through. Also like adiabatic versus non-adiabatic. So the first two is more like commonly described, but the adiabatic concept is more, it's new to people who are first getting touched in thermodynamics. So in this case, rigid and non-rigid means the wall is movable or not. Permeable, impermeable, transfer of matter. Adiabatic versus non-adiabatic, whether or not it allows transfer of energy. Right, so back to our example of the tea. Now, imagine my bottle, that's the kind of wall that's separating my system from the surrounding. And my bottle will be is it rigid or non-rigid? It's a rigid wall. It's impermeable, means it doesn't allow matter to come out, otherwise we'll have tea all over the place. And it does allow energy to pass through, so it is non-adiabatic. Right, so this is the kind of practice you can like try it on, like on your, with your colleague, like just point to a random thing and say like, hey, what kind of wall it is? All right. And then we have equilibrium. So 4 and 5, these definitions, we'll come back and revisit them later on after we've finished talking about entropy. But for now, I just want to expose you a little bit on the terms of equilibrium one time, right? And later on, we'll come back and revisit these definitions. So when we say a non-isolated system is at equilibrium, what effectively we're saying is that the system's macroscopic property will remain constant at the time. So when we say macroscopic property, again, that's something you can physically measure of a macroscopic object, like pressure, volume, temperature. Well, alternatively, like vibrational frequency, that's not a macroscopic property. And then removal of the system from contact with its surrounding will cause no change in the property of the system. So these two are the criteria of equilibrium when we're talking about a non-isolated system. And we have different types of equilibrium as well. So a thermodynamic equilibrium is stating the system is in equilibrium in all three criteria. So these three criteria, including mechanical equilibrium, so the system doesn't have any acceleration. And then you have material equilibrium, means like no net chemical reaction is taking place, and also thermal equilibrium. So the temperature is, well, adding a non-adiabatic wall causes no changes. Means like if we also allow energy to pass through between the system and surrounding, nothing will change. That means your system is already at equilibrium. And let's do an example together and see like what exactly does it mean, right? So let's say, again, we have this box of milk. So we can assume that the box containing the milk is rigid, impermeable, and non-adiabatic. Remember, these are the criteria describing the wall separating the system and the surrounding, right? So let's think about three different scenarios, and let's see like whether or not in these scenarios the liquid inside the box is at equilibrium or not. First of all, remember we have three different types of equilibrium, right? So mechanical equilibrium means it doesn't have any acceleration as compared to its surrounding. So in this case, if I just leave that bottle there without moving it, it doesn't have any acceleration, so it's naturally at mechanical equilibrium. Material equilibrium. Well, so in that case, what's going to happen? It depends on whether or not there's something going on inside the box, right? So if the milk is like going bad, it's in the process of like bacteria doing bad things in your milk container, then it's not at equilibrium. But in this case, let's just assume no reactions is taking place inside your milk box. And then let's focus on thermal equilibrium. So when your entire milk box is in the refrigerator and the temperature of your milk is 4 degrees Celsius, temperature in the refrigerator is also 4 degrees Celsius. So they're at the same temperature. Macroscopically speaking, we don't have a temperature change comparing to your system and your surrounding, right? So when we're having scenario 1, we are at equilibrium. What if I take the bottle of milk outside from my refrigerator, and now my room temperature is higher than the temperature of the milk? So energy will be flowing from your room atmosphere into your milk. So we're no longer at equilibrium. And if I leave my milk outside at room temperature for long enough, we'll eventually reach a new kind of equilibrium. So your milk inside and outside will reach this new thermal equilibrium as they have the same temperature. All right. Okay, so we have 2 more terms to go. These terms sound a little bit tedious. These are very typical things that you look at it, you're like, oh, this is straightforward, I know it. But do practice on it a little bit and get familiar with it, because we will start using these terms more often in the rest of the quarter. All right, 2 more concepts. And then we have different kind of thermodynamic properties. So we normally classify these properties into 2 classes. One is called extensive. So the full definition of an extensive property is one whose value is equal to the sum of its value for the parts of the system. Very long and jargon-like. But it's effectively very straightforward. Now, if you think about mass or volume, right, you have 2 different cups of tea. One is like 1 liter, the other is 0.2 liter or 200 milliliter, then obviously the mass and volume will be different for these 2 cups of tea. All right, so as long as that macroscopic property is changing with respect to the amount of substance in there, those are macroscopic properties. All right, you have mass, you have volume, like whatever things, or maybe like price, or like if you think about like you're buying like my tea using like money, like it's $2 per bottle. Then I'm buying like 4 bottles, then I need to pay $8. Right? So that $8 will be extensive because I'm buying more and paying more. Alternatively, we also have intensive properties. So these are the things that doesn't depend on the size of the system. So when we say something is intensive, it's more like pressure, density, or concentration, if you like. Right? Imagine 2 chemists, one at UCLA, one at Oxford, following the same protocol, preparing a like NaCl solution at like 1 mole per liter. Right? So they will have the same concentration. They'll have the same concentration of NaCl in these 2 cups, and thus concentration in this case will be our intensive properties. And again, I just like to use this milk example again, right? So you can have smaller and larger box of milk. So the mass and volume, also like the amount of money you need to pay, they're different. And pressure, density, these are the things that remain the same. They will be your intensive property. So what about taste? Taste of the milk, is it intensive or extensive? Right, it doesn't matter if you drink from a small cup or a bigger cup, right? So that's a more straightforward way to understand it. And one last thing about the system, we can have homogeneous and heterogeneous system. Now, for the most part of our course, we'll be focusing on homogeneous system. So when we say a homogeneous system, we're saying that each intensive macroscopic property is constant throughout a system. It's like if you think about a like diluted solution of NaCl, you took a droplet from anywhere inside that cup, it will always have the same concentration, same density, etc. And if you have like different kind of intensive property, then that's called a heterogeneous system, where you have like different homogeneous phases. So again, let's look at an example. They're so abstract. Now imagine you have a cup of still water, and we only care about what's inside there. It's just pure water, pure H2O, right? You only have one phase, which is the liquid phase of water, and this is homogeneous. And what about ice water? Obviously, now we have a heterogeneous system containing 2 phases, right? You have the ice phase and also the liquid phase. So 2 phases, heterogeneous. And what if I have ice soda water? So now it's still heterogeneous, but how many phases are there? 3, right? And that's all the vocabulary I want to introduce today, and see if we have any questions on these topics. Like these things are very straightforward when you know like you are talking about it and read about it, but take more practice for you to get super familiar with it. Yeah.
I have a question about the rigid versus the non-rigid wall.
Uh-huh.
You mentioned that your tea bottle is a rigid wall, but like you can move it around. So
no, okay, so I can move. So what I'm saying when I'm saying like rigid wall, I can move it this way, but my system is also moving with my wall. So I'm talking about the relative rigidity between my system and the wall, not like whether or not I move it on itself.
I have 2 questions. One, like going back to like the tea example. I understand how it's a closed system because the bottle is closed. However, with like since like, you could still like move like shape the liquid inside, would that also be considered like a transfer of energy, or like is it just energy with like in temperature reference?
So that's a very good point, actually. There are different ways of transferring energy. Like shaking it is also a way to add like mechanical energy into it, right? So later on, we'll see that, okay, transfer of energy from between the system and surroundings, one way of transfer of energy. But we'll see other forms of transfer of energy as well.
And one more question I had was like, with the example of like the milk outside, inside the fridge, or left outside overnight, when it comes to like assuming like the different types of equilibrium, I know like in these examples it was like all or nothing, like the examples. However, are there cases where like in some, like for example, it might be like mechanically equilibrium, but not like temperature-wise at equilibrium?
Oh yeah, that's totally possible. So that's why we have three types of equilibrium. Normally in this class, we'll have a lot of terms behind each equations. Like for example, we'll always specify like the system does not undergo any acceleration. So that's to ensure we're like set for mechanical equilibrium or so on. So you'll see that more often in later chapters when we have like things we specifically describe about the system.
And for walls, we should always view it in terms of the system, right? Not
Yes.
in terms of like overall in life. Because like, for example, if that crayon box or the chalk box was our wall, it could like not be rigid in terms of, or permeable in terms of water. However, in terms of the chalk, it is not permeable.
Yeah, so only in thermodynamics, always focus on what is the system you're trying to describe. All right, if we don't have any questions, let's move on to start talking about calculus. So these will all serve as review. It's like these are just basically your calculus, but in the more straightforward chemist perspective. Because in my case, I'm not a like math professor. I only care about how do we use calculus as a tool so we can understand thermodynamics. All right, so lots of people were like, this class is just a math class. It's not. Let's try focus on the actual physical meaning behind each derivation. But in order to follow those derivations, you do need math as a tool to go through that process. So let's do some quick review. We'll be talking about differential calculus, and as you probably know, it's basically just the slope when we're taking the separation to be like super small. So in this case, in thermodynamics, we will encounter rules of thermodynamics like the Boyle's law or Charles' law. We'll talk about them more next lecture when we talk about ideal gas law. Now in this case, if we're thinking about pressure as a function of volume, right? So in Boyle's law, which is an experimental observation that a super light gas will have this relationship of your pressure and the volume of the gas will have the product of a constant. All right, so the product of the pressure and volume of that gas of interest will be a constant number if we keep the system at constant temperature and the mass is not changing. So in this case, if we're writing pressure as a function of volume, then in this case, we have like basically constant over volume, right? And pressure is a function of volume. Volume is a function of pressure. And in this case, when we're taking the slope, well, you know how to do the slope of a linear line. It's y equals to mx plus b. And your slope in this case is just your m here. And if we move those separations between your x1 and x2 to infinitesimal small changes, then we have our derivatives. These are just very fundamental math. I'm going super fast, but if you need a little bit more refreshment in these calculus, a calculus textbook is way more helpful than our textbook. So in our case, again, we care more about how to use derivatives, how to use math as a tool for us to solve the derivation. So let's do some practice together to refresh your memory in how to do these differentials. For example, we have the chain rule. Like if you have a more complicated differential that you want to solve, Like if you have like sine 3r squared and you're trying to solve the differential of this function as a function of r, it's not straightforward to go ahead and just directly solve it, right? So you can write it out as say like z equals to sine 3r squared, and then we say like x equals to 3r squared. And in this process, this is what we want, right? So dz over dr is something we want, but we can't solve it directly. Instead, we can solve for dz over dx, which is basically d over dx as sine x, because we manually set x to be equal to 3r squared. And it's pretty straightforward to solve this differential. That's just cosine x, or if you plug in what is x, that becomes cosine 3r squared. The same applies to the second term. We have dx over dr. That's just d over dx, and my x equals to 3r squared. And solve that differential. That's 6r. So the actual product of these two terms then become our solution, which is dz over dr equals to dz over dx times dx over dr. That gives you 6r times cosine 3r squared. Nothing fancy. It's just like try to set up a model, try to use the chain rule. And I listed some common formula of differentials that we will use very often in this class. More might apply, but these are the major ones we will be using. And try to review it a little bit and see like you know how to find it. All right, so that's a normal differential equation, meaning we have one function that's dependent on one variable only. But in thermodynamics, we're often looking at more complicated systems, right? Remember, you have like mass, volume, temperature, pressure, all of these things contributing to the system all at the same time. So consequently, in thermodynamics, we will be using partial derivatives very often. So basically, a partial differential equation becomes useful when we're describing a function that has two or more variables, like z is a function of both x and y. So whenever you see this kind of symbol of the partial differential equation of z over x at constant y, so this is, we know that z is a function of both x and y, but we're keeping y as a constant and only looking at how z will change with respect to x at constant y. And vice versa, we can have dz over dy at constant x. All right, or in thermodynamics, when we're looking at like pressure, volume, and temperature. So if you see something like dv over dp at T, so that means we're looking at the change of the volume of my system with respect to pressure change at constant temperature. And if we are looking at one straightforward example, I already gave you the answer, but like if you think about z as a function of x and y, how do we solve for partial differential equations? Now, in this case, if we care about dz over dx at constant y, basically we're just keeping y as a constant and focusing on how z change with respect to x. So my y is always kept constant in this example. We're only looking at how does my z change with respect to x. And there are several things we will be using. There are several rules of partial derivatives we will be using in this class. And here is a quick list. I'm just going to go over them one by one. And when we come to actually use it in thermodynamics, I'll make sure to like also write it out for you to refresh your memory in what rule we're using. For example, when we're saying total differential of this function z as a function of x and y, what we're writing out is dz, or the total differential of z. That equals to the partial differential of z over x at constant y dx plus partial differential of z over y at constant x dy. You can have way more terms in this case, right? So now we only have z as a function of x and y. So what if we have an example, let's say, just randomly, let's say energy as a function of P, V, T, and N. Right? You can have like energy as a function of all of these, or maybe do entropy just to make it more relevant. So what is the total differential of entropy in this case? Right? You can have a question asking you write out the total differential of entropy, and the way to do it is just like pretty straightforward. ds equals to partial differential of s over p while keeping all other terms constant, so vtn constant, dp plus ds over dv while keeping p, t, n, and dv, and plus likewise ds over dt while keeping p, v, n at constant, plus ds over dn at constant p, v, t, dn. All right. So that's the first one, how to write the total differential of a term. And then there are several rules in partial differential equations that's telling us the relationship of these partial differential equations. Like for example, if we're looking at dz over dx at constant y, that equals to 1 over dx over dz at constant y. You're just flipping the top and bottom. And then we have this cyclic chain rule. So basically, in this case, where x, y, and z are the three terms that we care about, you have these partial differential equations timed together to give you -1. And they're also possible, like if you have 4 variables, 5 variables, this cyclic chain rule just becomes longer and longer and longer. But as long as you're alternating everything, it ends up to give you -1. And the third term here is if we're looking at the kind of chain rule we used before to solve for the normal derivative, the same applies to partial derivatives if we're keeping the same term to be constant. Let's say now hypothetically I'm looking for a change of z with respect to u at constant y. I can manually set like a new variable x and then solve the differential equations. So these are the things we will be using. Again, I'm not using it today, but it's important that you know how to do it when we actually start to working on it. And also, by the way, I do this pretty often, like just randomly write new things on the Blackboard. So that basically telling you like, okay, so I record everything. I also post everything. But I also will sometimes have new things coming up on the Blackboard. So if you're only watching the video, that might not be enough to cover everything. And I just don't have the mean to record what I write on the board here. So come to class as often as you can, but nevertheless. Okay, so let's do one example. I think we have time for it. Let's do this one. I have the 1.42 also worked out in the annotated note, so you can try it later on. So let's think about this one. Given that z is a function of x and y, so x to the 5th over x to the 3rd, can you evaluate the 4 partial derivatives of z and see whether or not you have this relationship? Because like if you took the second partial differential of z over dx dy, that should equals to dz squared over dy dx. So let's work on that. What are the 4 second partial derivatives available for this z? So we can have dz squared over dx squared at constant y, so taking the derivative all over x 2 times. We can have dz squared over dy squared at constant x, so taking the differential over y 2 times. Or we take the differential of z first with respect to x, and then with respect to y. Or we do that, first take the differential with respect to y, and then with respect to x. Okay. And I'm just going to focus on the bottom two, because you can try the first two yourself, because this one gives us a way to check whether or not our derivation is accurate. So when we're writing it like this, effectively what we're saying is we're taking the partial derivative 2 times. So the x is on the outside, and y is in the inside. So in here, what's the answer of this one? So at constant x, we're only taking the differential of z over y, and that gives us the result. So negative 3, x to the 5th will stay as it is, y to the 4th. Right, and then you're taking this, the partial derivative of this in with respect to x, while keeping y as constant. So in this case, my y will keep constant, y to the 4th, and x, you have a 5 in front of it, so negative 15 times x to the 4. All right. And if we do it the other way around, we have d over dy, and then dz over dx at constant y and at constant x. Now do it the other way around. You have d over dy, and what's in there? We're taking z with respect to x as a function of y. So inside there, we keep y as a constant, so y to the 3rd does not change, and then we have 5x to the 4th. And then you take the derivative of this formula, which is inside the bracket, over y at constant x. So again, we'll get negative 15, x to the 4th stays the same, y to the 4th. And these two results should be the same to each other. Okay, how are we doing here? It's just calculus review, right? It's okay if you feel like a little bit slow in solving these calculus. You'll get better along our way. Yes?
So I remember back from Calc 3 that there are certain conditions where the mixed partials aren't the same. Do we ever need to worry about that?
No, I'm not your math teacher. So we'll only use like very, very basic calculus. So we won't have like super extreme scenarios. Yes? Which one is the A and C? Sorry, can you repeat the question again?
On the previous slide, there was a closed review that derived the following equation.
So this one?
Yeah, you should go over A.
Okay, so A basically is like partial derivative of z over x at constant y, right? But what if I want the x dependence on z at constant y? So just like flip the top and the bottom. So that's the first one. The last one is like the chain rule we used. It's a way to help you solve partial differential equations. It's like you can have a hypothetical like variable x in this case if we're solving for z over u. Yes?
So I'm looking at this, and it seems like if you were to like substitute C into like B, then you could get every single
Yeah, they should all work together.
But I'm wondering where the negative sign
Oh, that's too much math for this class.
should be. Okay.
Yeah, you can have extended reading back to the calculus textbook in where that negative comes from.
Okay.
Okay, so we have about like 7 minutes left. Let's just quickly review on integral calculus as well. So for integral calculus, it's the other way around, right? So in differential equation, you're breaking the system into like infinitesimal parts, and the integration is add them back in. You have two different types of integrals. You can have definite integral, so you're actually solving it from like range A to B. You can also have indefinite integral. We're just getting a regular expression of the results. And these are just, your equation sheets from calculus. Again, we won't be using everything on this page, but it's just like a quick refreshment in what might be needed when we're talking about integral calculus. The best way to keep track of all these equations is to come up with your own formula sheet. I will have a formula sheet for you, and you can also download it. That's coming from my end, but it's always helpful to write down things you think it's important for you. And that formula sheet will grow longer and longer throughout the entire quarter, but you are the one that's more familiar with that formula sheet. So yeah, these are just like general equations that we will be using throughout the quarter. And let's try one example together and see like what exactly do I expect from you when we're talking about integral calculus. So let's see this one. I have several examples. Okay, let's do this one, 1.65. So given a differential equation, so remember when we were saying like the differential equation, we're talking about how does my fx change with respect to x. So in this case, for example, in the ideal gas law, you can imagine this one to be your volume and your x to be your pressure at constant temperature. It's changing, right? So experimentally, we can observe how does my fx change with respect to x. But as chemists, we care about the actual relationship of my fx. So that's where we use integral calculus. So let's look at the first one. Given that this differential is solved to be 2x to the cube plus 3 exponential 5x. So that's, for example, something you experimentally observed when you have like, when you're measuring fx and changing like x to different values. And in order to solve for what is my fx, we basically just write like the fx. I'm moving my term of the x to the right-hand side. So 2x to the cube plus 3 e to the 5x. All right, I'm just moving the x to the right-hand side. And what we can always do is integral on both sides. So what that means is adding an integral on both ends of my equation. So we have integral dfx equals to integral 2x cubed plus 3e 5x dx. Now the left-hand side just becomes fx itself. And on the right-hand side, well, it's just solving the integral. So the 2x cubed integral becomes x fourth over 4, and basically becomes like x fourth to the over 2, and plus 3 e to the 5x over 5, plus some kind of constant. We will do partial differential equations, but we probably won't do like multiple integration when we have multiple variable. That's a bit overcomplicated. And also like now if I tell you we're looking at x from x1, say maybe equals to 1, to x2 equals to 2, right? We can make it a definite integral and plug in numbers to solve for the actual fx change between x1 and x2. Okay, I think I'm running out of time. Again, I will be in my office today if you have any administrative questions you want to ask. And I'll see you on Monday.